Okay. Hi, everybody. Welcome to QASIG. We're going to get started in just a few minutes. We're going to let our attendees join us, and then we'll be getting started. Looks like we have a great audience tonight for Harry and Doug, so we're excited.
Very excited. This will be a great talk.
Good. We're hoping so.
All right.
We've got a full house tonight.
Yep.
Yeah. So Shelley, it's okay if I quote the comment that came into us as I don't actually have the attribution on it, but I could.
For sure.
Okay.
He did ask us to share it with you, so he wants you to know. So yeah.
Okay, good. And that's Drew Cooper, I think.
And I don't know if he was going to join tonight or not, but yeah, I think it's fair to share.
Okay. Sounds good. Sounds good.
Yeah. All right. Jim, do you want to get us kicked off?
You bet. I will get us started. I'm Jim Frazier, and I work with Cordev. And I'm just going to be going through some of the housekeeping for this evening. I think everybody is fairly accustomed to Zoom meetings these days, so maybe not necessary, but just to let you know. Once we get started, everybody will be on mute, and the presenters will give their presentation. At the end, if you would type your questions into either chat or Q&A, we'll pick it up on either side. I will kind of go through those and allow them to respond. If we have time, we could also go to open mic if that is appropriate. So I do have a kind of a question. This is a very unofficial survey. You know, we've been doing the QASIGs virtually now for a while, and it's been great because we can reach out to a bigger audience, we pull people in from different parts of the country. But I'm just kind of curious for the attendees, as we go forward, and I can see the light at the end of the tunnel, and we will soon be at a point where we can rehost these in person at the shop. Would most folks still like to participate virtually, or would people like to come in and be at the shop? And just send us a note at some point in time, or add it into the comments, and I'll pick those up. But that's very unofficial. I'm just kind of curious which way people would like to do this going forward. And now I'll turn it over to our founder, Joe Dillon, for introductions and then our presentation.
Yeah, and I'm sure there'll be a mix. I mean, the cool thing about having these on Zoom is that anybody from anywhere can join in. And I love that. And people from all over the country or the world or whatever can participate or even just catch up later. But the cool thing about being together is that there's more of a networking opportunity, and you hang out, have a slice of pizza or soft drink or beer or whatever, and get to know each other. But both sides work, and I think the combination going forward will be super cool. But anyway, I've been excited about this talk for a couple of months. Harry Robinson, who's spoken before, and Doug Szabo, both great guys. And it's a really intriguing topic, I think. Test generation techniques, which is always valuable. And then the one that I'm really intrigued to see what this is exploratory automation, because it seems like they couldn't be on further poles from each other, but I can't wait to see where it goes. I hope you enjoy it. I'm going to go off screen and let our presenters take over the whole show.
Thanks, Joe.
Enjoy it.
Okay. Can I share here? Okay, can you all, well, can some of you see my screen?
I see a slide.
All right, that's good. That's getting us in place. Okay, so welcome folks out there in Zoom land. Doug and I have been doing a bunch of exploratory test automation for several years now. A couple years back, we did exploratory test automation on sorting routines and found it to be very useful and fruitful. So for the past couple of months during lockdown, we've been working on a way to actually improve the way that testers can do exploratory test automation for state models, which is something that's been close to our hearts for a long time. First, let's talk about what is exploratory test automation, because it is a controversial topic. So I've got a couple of pundits up here, and part of the difficulty in assessing exploratory test automation is what people mean by it. So Dot Graham, should automated tests should find bugs? No. And yet she is a fan of exploratory test automation. And that comment is actually saying that she doesn't know that she wants automated tests to be there to find bugs or simply to show the stability and quality of the product. Kem Kainer, who invented the term exploratory testing back in '84, I think. He is now a big fan and has been a big fan of computer-assisted testing. And like the rest of us, he's actually struggled for what exactly the term should be. If you've heard of HIVAT, high volume automated testing, that was Kem's particular take on the topic. And one of his talks, or several of them, were about how to apply that kind of computer-assisted testing. And one of his comments was, if we had a way to generate and oracle skrillions of inputs, how would that actually change the process? Tricentis is a company, I don't know who it is there that talked about it, but exploratory testing by definition cannot be automated. And in fact, we agree with that. And what we're doing is not actually automating the exploratory part, because the exploratory part is about people thinking and making their decisions on what seems to be the next best thing to be doing in the testing. So we actually agree with Tricentis on that, but we agree more with Michael Bolton underneath there in blue that says automating exploratory testing is impossible, but using automation as part of an exploratory process is entirely possible. And that's really where Doug and I come down on this. What we have been doing is building a system that makes it easier for people to create and manipulate occasionally very large state models, because the kind of state models that you could do by hand or do in your head are typically not going to be detailed enough to find many bugs. And so what we have been doing with what we've been calling Easy Model is creating a way to use state variables to create systems that are large enough to find bugs, large enough to convince us that the system itself is significantly stable and not just stable in the parts that we've been able to reach through manual exploratory testing. So that's really what this talk will be about, is the work that we've done toward that tool and how we are looking to help to make that tool help support exploratory test automation. And then finally, as soon as our blurb came out for this talk, we got feedback that said, please let the speakers know that they are confusing exploration with non-determinism. And now, as somebody with a liberal arts degree, I love that sentence. But they are very different concepts, and it insults all the smart humans doing exploratory testing today to equate them with fuzzers or monkey testing. So here, we kind of agree with this. And what we are doing is not so much using the smart humans to be fuzzers or monkey tests, but to put tools in the hands of the smart humans that will do a bunch of the work for them, much in the same way that fuzzers or monkey tests do all of those kinds of inputs. So a way to think about it might be more like what we're trying to do is create something that's the equivalent of a chess engine. In chess now, people do what's commonly called blunder checking with their computers. You are looking at a particular strategy and you've got some moves planned. What you can do is actually put that into your chess engine, and it will go through exploring all the combinations that could be happening, and it'll let you know if you're actually walking into some sort of a trap. So that's part of our vision of this tool, is that this tool is here to help you see further down the line on a bunch of the ways that the combinations in the system might actually cause a bug. So for the example that we're going to work through, this is one that Doug and I have been using to make sure the tool is doing the right things. So a REST API application that maintains a to-do list. And this was inspired by a bunch of work that Alan Richardson has done in his YouTube videos and supporting documents on exercises for how to test a REST API. But as far as we're concerned, what we are interested in are the things that, let's say our team has been tasked with developing and creating, testing the to-do list application. There are going to be actions a user is going to want to do, like with any to-do list. You want to be able to start the session so you're actually talking to the application. You'd like to add a to-do item, edit one. You'd like to delete a to-do item when you no longer need to hang on to it. Resolving is what you do when you have finished the activity for it to do. So previous to that, it's active. When you resolve it, you say it's done, although it's not yet deleted. Activating a to-do is typically what you do if you have resolved a to-do and then you realize it's not actually done. And now you need to activate it, put it back into someplace that it's catching your attention that there's still a task to perform. And then retrieve a to-do, list all to-dos, just kind of the regular kind of query things that you say, tell me what the status is on this particular to-do, or tell me how many to-dos I've got. And then a way to end the session so that you're no longer talking to the service, and the service then should be hanging on to your to-dos in some sort of persistent manner. Okay, so with state variables, state machines tend to get really big, and they're a great way to do testing, but a lot of people shy away from them because you don't have an easy way to manipulate that many different states and the actions between them. So in model-based testing, the state variable approach says, break it down, each of the actions and the states in the system, break that down into state variables that will hold part of the state. You can use those state variables and their values to then say, what am I able to do given the state that I'm in? And then what happens, given the bunch of actions I've got, if I choose an action and I execute it, where do I then move to in the state model? And these two questions are so central that it might as well just be on either side of an index card, because you can walk through an entire exercise that says, here I am in a state in the model. What actions are available to me? And then, okay, if I perform this action, what happens? Where else do I end up in the state model? So let's actually start modeling this thing. So we want to figure out how to start a session and how to end a session. So we create a state variable called in session. And that's either false when we're not in the session or true when we are. And the way that you get between them is that you start the session. So when can I start a session? Well, if in session is false, then start action is available. It's possible that you can run the start action, if the session is already happening, and then typically the system would ignore it since you're already in it. So it would end up being some sort of no op. What happens in the model when I start a session? Well, in the model, you were in a state that had a state variable in session set to false. All that happens is actually it changes the in session variable value to true. In terms of now on the right side, when you want to end a session, okay? So when do I end a session? Well, if I'm in a session is true, then the end is available to me. So end action is available. And then where do I end up? I end up with that variable getting set to false. So this is really the crux of model-based testing with state variables is you have a small number of variables, each of which has a very simple behavior that you can check, and you can have the computer check for you as well that you're handling everything correctly. So now the one thing that is interesting here is that this bit of pseudocode is almost exactly what the code is. So to do this, you're actually writing some code. Currently we have it in C#, but it looks to us like one should be able to write these conditions in Gherkin as well. And you're writing rules that will actually implement the state variable manipulations for you. And so these rules can actually then produce this particular graph. So this graph is what you see if you actually put in this particular very simple model into Easy Model. And what it does is it says, okay, it gives you the two states. It tells you how you get from one to the other. It tells you what state you are currently in. When we start off here, it's going to be the initial state. But as the system moves along, it will, depending on the setting, it'll either tell you what state you've arrived in, or in some of them, it actually tells you what the transition is that you've been executing. Over on the side, what we do is we're tracking coverage in terms of hit counts on transitions. So right now, the transitions are black because we haven't done anything. Once it gets hit, it'll actually turn into whatever that is. Magenta?
Magenta-ish.
Okay, sure. And it'll pop up a little number in parenthesis that'll tell you what the count is on how many times you've hit a particular link. It actually goes significantly high. We have it stopped at 5 just to make it easy to see that you've actually reached, you've hit things 5 times for the transitions. This is important because what our algorithm for coverage does is actually it moves around in the graph looking for transitions that have a low count, and then goes and visits them and moves up their count. And the whole floor of coverage. So right now, if you look at this, it says the hit count floor. The floor is 0 because there is some transition in the system that's got a 0, and we're trying to get everything in the system to a 1. In this simple example, it doesn't look that difficult, but it gets more complicated. The fit graph, this is actually just a little movie of it, so the buttons don't actually work. What it does is it actually takes the graph, makes it all fit into the screen. We like to run these quite a bit, so reset on the traversal simply does what it says. It cleans off all of the hit counts, and we can start again. And then just some debugging. So the graph elements, there's 2 nodes, there's 2 edges, and there are 2 actions. So this is not a thrilling part of the video yet, but those may come. So we kick it off, and it executes the start session, it executes the end session, and we're done. Not a very exciting test, but it's not a very exciting application that we've implemented so far. There we go. Okay, so now let's start getting to the actual what the system does. So we'd like to add a to-do item. Currently, the previous one doesn't even have any notion about to-do items. So now we're adding the to-dos state variable, and it's actually a counter, so that we start off with the number of to-dos being 0. When you add a to-do, then you increment the count by 1. So when can I add a to-do item? Well, if you're in the session, then it is available to you to perform the add a to-do action. And what happens when you do add a to-do? Well, then the number of to-dos goes up by 1. Now, as far as the application itself is concerned, it doesn't have any upper limit really, until you choked out the amount of space on your computer, I suppose. Since we're doing testing, we don't necessarily want to leave that unbounded. So what we do is we artificially put in a max to-dos, because this will restrain the explosion of the state model. So currently, let's say that we only want 1 to-do. It's a very simple to-do list. So only want 1 to-do in the model that we're going to generate from our rules. To delete a to-do item, okay, so it's like the add but backwards. If we have 1, then we can delete it, and we get 1 less. So when can I delete it? If I'm in a session and the number of to-dos is greater than 0, then I can delete. And what happens when I do? Then the number of to-dos goes down by 1. Okay. So looks like I already executed this. So we'll give this a try, and this will walk through. There we go. And so this will walk through, and as it does, it increments the count on those links. Okay. And so it hit every one of them once, and that was the target for the floor coverage. So we are in pretty good shape there. Okay, so let's continue building. Here's why we care about the max to-dos. Max to-dos equal to 1 is not actually that interesting a test. We'd really like to see that this thing can handle a significant list. It may be that some of the list implementation is incorrect, but it's actually more likely that we're going to take some sort of performance hit if we get to very large lists and do a bunch of manipulations with them. So we like to start off with something low. So, okay, number of to-dos is 1. And that means we have a very simple graph. If we have the max to-dos set to 2, well, now we could have the 0 to-dos. We could have 1 to-do. If we leave the session at that point, then it persists offline with the to-dos 1. If we add in a 2 and go off, then we're off with 2. Again, with 4, it grows. It is very easy with easy model and changing the value of the max to-dos to actually make this large enough that it becomes difficult to see the graph and see what the values are. And so we provide a way for the tester to actually zoom in and see what the values are on the nodes. Okay, so let's try this one. Okay, and again, the system is generating its traversal, and notice that don't know it, but we haven't actually changed the algorithm for doing the traversal at any point. What we've done is we've changed the state model, and then the algorithm is going through and making sure that it has the coverage. So this becomes important because it means that the algorithm can adjust as we have to grow and shape the model in the directions that we want. Okay, next, resolve a to-do and activate a to-do. So we resolve an active to-do, and if there's active to-do items, then okay, we can resolve. And when we resolve them, then what was a active to-do becomes a resolve to-do. And then the other way is the reverse. When can I activate the resolve to-do? So this is when something has been on the list, we have resolved it because we think it's finished. Turns out it's not finished, so it has to get reactivated. So if there are resolved to-dos, then we can choose to activate one of them. And again, the number of active to-dos goes up by 1, resolved to-dos goes down by 1, because that is the trend, that's the transaction between those two lists. Okay, so now, if all we're going to allow it is to have one to-do in play, then the two lists of the to-dos, resolved and active, are going to have to trade back and forth on it. Okay, so there, we've got that done. If we now increase the maximum to-dos to 2, then we're going to cover this as well. So this begins now to lean toward the exploratory part of this, because now that we have a couple of dials that we can turn, we can change the elements in the graph. We can change the number of to-dos that are going to be available. So now, if we think there's a performance problem, we can grow the size of the list that we're willing to support. So, oh, there we go. So the previous ones went along because I had been clicking that when I recorded this. As we get to this point, it's now no longer useful for a human to actually try and go through and click on these, which is why we let it do that automatically. Now, this is just the model. This needs to still be connected to something that tests the system under test. So as it executes an action, then the action gets passed along to some program that translates, for instance, add a resolve to do. So that will get handed off to a program that actually knows how to interact with the system under test and creates a to-do, in that case, in the resolve state. The test, the adapter can then oracle the result, because it knows that, let's say that I was in the state where I was in a session and I had no to-dos at all. I added a resolve to do. I should still be in the session, and the active to-dos should still be 0, but there's an increment on the resolved. And so this is wonderful because this now allows the system to actually do that verification itself. And although it's not always possible to verify everything about the system, this is very useful because this will detect the issues. A time when it's not possible to easily verify everything is, for instance, if the session is not running, then it's very hard for us to know what the values are in the counts that it was storing, unless we try to read them ourselves, or in fact, you do the more typical thing, which is that you start up the session. Okay, so now with, actually looks like the wrong graph. So being that it is just a slide, we could actually go to the, oh, okay, yeah. This is the wrong graph, but it's pretty.
Which one were you looking for?
There should be a max to do set to 3, I thought. That's okay, we'll get to it. Okay, so we can actually go to the, let me go here. So I may be able just to run these right from my spot, Doug. Okay, so here is easy model, and it's generating the the graph, and it will also generate the traversal. So okay, well, that's kind of quick. The speed is adjustable on this, so straightforward enough. Here is a very similar graph, but now we have also added in the edits. So there's in any state model, there are going to be a bunch of transitions that actually don't take you to a different state. And so we refer to those just as self-links, that it's just coming back to the same state that it was in. It's useful to test these, but it's often advantageous to it's advantageous to be able to turn them off, because in this to-do list, I think there's a total of maybe 10 self-links per node, which means if you run the traversal, that 9 out of 10 transitions that it's going to be hitting are going to be self-links, which tend not to have as many bugs as you'll see in the transitions that actually take you between nodes. So 60 is a little fast for this, but okay. So if you saw that fly past, so what this has done for this small graph is it's actually hit all of the links at least 5 times. It actually hit this one 6, but we actually saturated 5 so that it's easy when you look at it to say, oh, okay, the system has actually hit all of those things at least 5. I could do that. Okay, so here is the active and resolved. And okay, so this is the one that's just with 1 to do. Okay. So here's a slightly more interesting one. So complex enough. And it has a floor of 5. So okay. So again, we didn't have to do much with that. We hope you consider this exploratory testing, in that we are making the decisions about how many links to involve in the model, how many to-dos, how much coverage we actually want. So have to move us around a little bit here. Doug, do you have a?
Yeah.
Okay, there we go. I got it. So, okay. Well, I'll tell you what would be a useful one? Doug, can you set us up to look at something that is lots of to-dos so that people get a feel for the size
Sure thing.
that we can do with this?
Here we go. So at the moment, Harry, I'm zoomed in here on the beginning of the graph.
Okay.
So this is one that has a little bit more state than the ones you've been showing. In addition to the resolved and active to-dos, we also have the idea of authorization and passing a secret note. So that gives us a little bit larger of a graph. And this one, Harry refers to as the Hotel California, because we enter into an area and for some reason, we don't end up exploring or covering the entire graph. So we'll let that rip. And a whole bunch of the graph, all that gray stuff in the middle and bottom, that never got traversed. And the reason, if we look in closely, is that there's a piece of state, which is the authorization token. And when the authorization token gets set to true, there's no way to get back to where the authorization token is false. And it just happens to be the system design. And if we could be able to set the authorization token to false, meaning we would give up whatever elevated privilege we have, then we could get back to the remainder of the graph. Back down here. And we could cover everything.
Right. So in this instance, having the model, the graph, is actually useful as a spec review issue, in that just as we run it, we can see that the graph is not strongly connected. You can't get back to everywhere from everywhere else. And as Doug said, it's equivalent to if you had elevated your privileges, you couldn't lower them without actually having to log off of whatever system you were on. So it's worth just at that level bringing it in front of devs and system engineers to say, is this the intended behavior on this? How about one of the very big graphs, Doug? Oh, there we go.
Yeah, there's one. Now this this big one, interestingly, the difference between it and the previous one is that we've added the ability to release the authorization token. So now, when we traverse this thing, we'll just go through it at high speed. We see that the entire graph gets covered. So adding that one capability to the system would solve the problem of being able to get from one place to another as far as state goes. Yeah.
And actually, what we find interesting is that in this situation, typically somebody would have noticed that there was no way to get out of that escalated privilege situation, and therefore the release token would have been brought in, later on in the development. With typical automation or with manual exploratory, this would have caused a problem, because now people need to take into account that there's a whole nother transaction going on in the system that they then have to say, okay, did this break anything? With using the models, not only are we able to say, you know, there's something that looks wrong with the way the system is behaving, but if they do decide to actually implement the release token, we're already in a position to have it tested because it just fits in as another, you know, link in the system for us.
Now I do have one that's has even more nodes. Let's see, I believe this one. Yeah. So this has 306 nodes in it. And what it is a explicitly representing a to-do list of up to 16 items, and then being able to go and do anything you want to any of the items in the list. So it would take 1,125 actions at a minimum to go and cover all of the possible changes you could make without really considering variations in the input data. So it's a lot of testing for to get the coverage that you'd want.
And what is interesting about the algorithm that we're using to do the traversals is that it is intentionally aimed at not being repetitive. So a Postman traversal is an algorithm that gets you through a system in some minimal number of steps. What this does is it randomly chooses a transition in the system from where it's currently standing. It chooses a low hit transition somewhere in the system and then makes its way toward there. So we refer to it as the random destination postman. It's as if the postman in your town didn't actually just walk up and down the streets, but actually looked in his bag, read the address on the letter, and started walking toward that person's house, delivering other mail on his way. It'd be a terrible way to be, you know, a postal employee. But in terms of what we're trying to do with this is the system is always choosing new paths through. So if you run this same transition, unless you hang on to the randomization seed, you'll rarely get the same exact steps. You will get the coverage. And so there's a difference here in terms of the kinds of things you can do with this type of testing versus regular automated, you know, stuff that you write out every step and then, you know, lock in the way that they execute. This system can do that, but what we like is it actually is more useful to us because it doesn't actually just follow in the steps that it did before. Another difference between this kind of automation and other automation, what we refer to as static automation, you know, some bunch of steps that are written in a script and that run. What's different with this is that for a lot of static automation, you have to wait for the system under test to actually stabilize. And developers and system engineers don't necessarily like you to get in and start testing because they may actually change the design between one time and another. And they're afraid that if you write static tests, that there'll then be something that keeps them from moving forward with what they think is a better design, a change in the design, because the tests will break.
Yeah, it's a lot of maintenance for the automation programmer.
Right. And so an advantage with this system is it's so easy to change. As you saw, we've essentially assembled the system in a way just in the past hour or so from bits and pieces. So what this means is that you don't have to actually wait for development to be done with their stuff. You can actually keep pace with development. So the phrase I like is that static automation, you wait until version 1.0 before you actually start doing any automating. With test generation like this, you can actually start at version 0.1, because even if they scrap the design and just go in a different direction, because you're doing generation of these systems for doing the testing, you are just as happy to move on as they are, because there's not that much of a cost incurred.
True.
So we could show you some more graphs and traversals. Are there questions? This being such a controversial topic, we'd like to handle some of the.
Yeah, Jim, do you have something for us at this point?
You bet. And for those in the field, please feel free to enter your questions in the Q&A or the chat. We'll pick them up in either side. But Keith did have the question a little earlier on. I didn't want to cut you off at the time, but he was curious if you could force transitions or do multiple starts.
Yes. We can force transitions easily. What by multiple start, Harry? Do you know what?
I'm not sure what that means. Can you give us an explanation of multiple starts?
Keith, I am not clear either. Please let us know if you can define that, and we'll see. We'll circle back around and see if we can have them address that for you.
We could have Keith speak if you want to open up his mic. If he wants to speak, that would be great.
And I'm not sure that I have access to open his mic, Shelley. Can you open the mic?
I think I have a mic.
There we go.
Okay.
So I don't necessarily consider it a flaw that they didn't allow you to reset the auth token without logging out. And going back to that graph, if you could start different ways, then you could cover the rest of that graph. The graph
Yeah, with a restart, yes, that's true.
So if you did different starts, and if you could force which of those ones it went to, then you could start covering some of those other areas.
Correct.
That's correct. Yeah. Yes.
Yeah. What we're saying there is that we raised the issue. It seemed suspicious to us that was the case, and so we at least get the question out in the open line. Is this what we intended to do? Or did somebody just forget to put in the line that says we should be able to release that token? So yeah, a useful part about doing this kind of testing is that because it's a development effort of its own, it becomes then a conversation, not so much about I found a bug in your code, but I see something suspicious and I need an explanation so that I can actually implement my code to do what we're supposed to do. So it's one of the things about models is that it gets everything out in the open so everybody can actually just kind of stare at the same whiteboard, or I guess now Zoom screen.
True.
Yeah. I have an answer for Alexis. How do you make sure you don't have defects in your model? I see you are basically testing the program by implementing an analogous algorithm to itself. So what we are doing is actually, so anyway, thank you for the question. What we're doing is actually implementing a very high level of the functionality to it. The developers, 90% of what developers do is actually plumbing. They've got to make sure they're connected to the network correctly, that they're connected to the database and such. Our work is actually at the functional level, and it's therefore a lot easier for us to do quickly, change quickly, and because it is different than what they tend to be doing, we then are able to, it's kind of like two rough surfaces smoothing each other down, because we go to them and we say, your code did this and my model thought it was going to do that. And then there's a discussion, because either the dev has to change their stuff, the tester has to change their stuff, or they both realize that they're off on something and it gets straightened out. So
yeah, Harry, I brought up the client program listing in my share, just to address what you're saying about high level compared to what the developers are going to do. So in our program that causes the graph and the traversal, we think about the state in the implementation that's of interest to us. And so we don't actually have all the structures and minutia that are in the system under test. We have abstractions of everything. So when the developers write a whole bunch of code to go and modify the to-do list, we just have a descriptive idea. And then we go down and we have a function. Let's go to given a particular state you're in, what actions can you take? So pretty simple. If you're not in the session, you would start a session. Once you're in the session, you could get the to-do list, you could show documentation, get the heartbeat of the service. And then if you actually have either active or resolved to-dos, then you could edit some of them. And these functions end up being, well, we don't actually implement the function, we just have the idea. So it's more of a mental game where we then go to the end state and we say, all right, so if the action was that we started a session, the consequence is that we are now in the session. So we don't have to spin up an HTTP server or anything like that. We just change the state value to the way it should be according to a spec. And then we challenge the system under test in some way to see if it actually is that way. And there are occasions where the model is wrong, absolutely. In fact, we made some corrections today to that effect. And one of those was right here. The edit some to-dos was always available. And then it became apparent in the visualization that we were able to try to edit to-dos when we didn't have any to-dos. So then we added this guard code to say, well, if you don't have anything at all, then you can't do any editing. Once the guard code was in, then we got a better representation. And so that's the level of sort of debugging that we do on the test model versus the implementation. And
so Doug was pointing to a bunch of code that talks about all sum. What that is an abstraction layer that we're working on. It's lovely to see enormous graphs, but it does get kind of clunky to actually have to work with them. So what we're doing is creating a state machine where you either have no to-dos, you have the maximum number of to-dos for the test system, which means that you don't want to add any more. So those are two states that are different from the place where you have some, where some means more than one and less than max, because in the sum state, then you can delete some, you can add some. In the zero state, you can't delete any. In the max state, for the test purpose, we prefer that you not add any. So it tracks the abstract state about how many do we think there are. And then we actually have the number that's being tested. That's actually handled more at the adapter level, so that the model says, delete some of the to-dos. And so the adapter then says, well, I've got 17 to-dos out there. I can delete up to 16 of them and still remain in the sum category. So that's under active investigation by Doug and me. Okay, Rob Sab. Hello, Rob. So here's a concern. Your tool seems to be excellent at applying different strategies to traversing a directed graph. Thank you. But you seem to focus exclusively on state models. So in fact, we don't. This is particularly good for state models, you're right, and for state transitions. But a way to think of it is also as a delivery system, because, for instance, the edit function, the query, a number of different things happen at the nodes. And so, for the edit, you're entering data. So what you have there is actually a bunch of testing that is making sure that people can enter the kinds of characters that they think they can enter into that to-do. And so we did this. I had an intern who wanted a job with Visual Studio back when I was at Microsoft. He wanted to intern with them the following summer. And so what we did was we actually hooked up a traversal algorithm to a monkey program, which then navigated its way around Visual Studio. And whenever it found any place it could provide inputs, the traversal program would call the monkey, and the monkey program would beat on the Visual Studio interface. He found 4 crashing bugs, I think, in the first 15 minutes. It actually took us longer to make up the slides for the presentation he did to Visual Studio than it did to find the bugs, and it took us not much longer than that to actually write the thing. And he ended up interning with Visual Studio the following summer, and they asked for a copy of the slides immediately.
So Harry, I don't know if the audience is how interested they are in this, and we are getting close to the end, but this huge graph with the 306 nodes representing 16 to-dos maximum, the abstraction of it gives us this graph, which has only 18 nodes. And with the abstraction, we represent any number of to-dos, going from 0 to sum to maximum. And then the interpretation of 0, sum, and maximum is up to the adapter code. And in the adapter, we write loops and use structures of arrays, which are all easy to work with as a programmer, and we don't have to try to visualize them.
Right. And so, for instance, for this abstract system, we could easily have a to-do list of 10,000 items, where that would actually be a little awkward to have to handle if we were tracking every item count number as a different state.
But it would be this graph, even with 10,000 or 100 or 2, and then the code. So here's the implementation of the adapter that connects to the system under test, doing the action of deleting some active to-dos. So the code has to have an interpretation of what some means. And the idea is that if you delete some, you want to have enough left over so you could delete some more later. So if we have less than 2 to-dos remaining, then we won't do this action because it wouldn't give us any more to delete later. That's actually a problem. If we have at least 2, then we randomly pick a number to delete. And then we set up the, it's an HTTP server, so we set up the headers. And then we go through the collection of to-do items from the server. And we go through and we're deleting the active ones. So we find one that's not yet done. And then we pop in the ID telling it what to delete and ask it to be deleted. And if the system under test can't do that, then we have a failure condition we can report on. If it does do it, then we take care of our counters, which is the complexity of our program. And once we've gotten through the quantity of items to delete, we go back and tell the model that we're done, and we compare the end state to the model state. And if everything's good, then we continue to the next action. So
yep.
That's the automation of it all.
Yeah. Okay. And a question from Brenda Stensland. What is this app we are looking at? Open source tool? So this app is what Harry and Doug have been working on during lockdown.
Yeah. we had some time.
And we have for quite a while wanted to have a simpler way to create these kind of state models that in a way that doesn't require a lot of the plumbing programming to happen. And so
the thing that's animating on the screen right now is just an HTML file that has a batch of JavaScript in there to tell it how to animate. It's really a recording and playback of what we calculated with the model. So the HTML file, Harry, if anyone wants these, do you want to make them available for people to pull down and play with?
That sounds fun. With the request that if you see issues or you see things that you'd like to work differently or better or something, that you let us know. But yeah, that would be great. Lots of eyes on anything makes it better. Is it actually doing execution when it runs? At the moment, no, but Doug is working on the adapter that will actually do the execution. It's, for this part, it's more useful and critical to actually make sure this part of it works. What we do is we think of it as the model is talking in kind of model language, and then that just becomes a simple translation, maybe even just through a big switch statement, so that when this thing says, do X, press the button in the GUI, that could then get translated as, when they say that, then I do this particular Selenium call.
Yeah.
A way to think about it really is that you could actually, if you had an intern that you didn't like, you could actually have him take the output from this and actually do all the actions for thousands and thousands of steps, because all it's really doing is telling something how it should be behaving on the conceptual level with the application.
Yeah, so Selenium or SmartBear or whatever the toolkit is that you like to drive your testing with, you would hook up the sequence of actions to it. So there is, depending on your tool choice, there is either a little or a medium or a lot of amount of code to write for the actual execution and comparison.
So we are getting pretty close to time, gentlemen, but Harry, did you see that Alexis had one more posted that's still open question, and that'll probably be about the last one for us this evening.
Okay. I can foresee a unique top-level algorithm to be written between devs and QAs, which in turn would probably mean that if my model is correct, then I can only find bugs that are completely independent of it.
Well,
go ahead, Doug.
Maybe,
so I'll let Dev give you the dev answer, and then I'll give you the tester answer.
Yeah. I worked on a model for an installer once upon a time, and it ended up finding memory leaks in the installer, even though it wasn't looking for them. So the requirement for the installer said that you could click this button that would cause the installation to begin, and the button was still available after you clicked it. So, you know, the model is pretty crazy and it'll do what it's allowed to do. So it clicked install twice, and that caused a hang. And I took that back to the developer, and he said, well, you're not supposed to do that in the first place. And I said, well, the hang is kind of the problem here. And at that time, that product was in production, and customers were complaining that they couldn't upgrade. And we couldn't understand why they couldn't upgrade, because it worked for us, you know. So we went into the field, and sure enough, we would look at their computer and they could not upgrade. And the development team didn't know why, but we took the model program and we put down version A and started the model against the installer. And then while the model was running, we put down version B and let it see if it could update, and it couldn't. And it found the memory leak, which the installer itself didn't actually exit properly. So all these customers, you know, you leave your computer on forever. They would install the version they got first, and when they got an upgrade, they couldn't run the installer again because it was already running. The previous one had leaked and the process had not exited. So yeah, it does trip over things, whether you've designed it to look for things or not. And that, I believe that has to do with the way that we just let it do things randomly. We don't try to focus on something because we don't actually know where the bugs are, right? We want to spread out the activity.
Yep.
And now the test answer.
Yeah. So I think that dev thought and test thought are so different anyway. It's just different perspectives on it. So there's usually a bunch of good cross roughing or something that that we tend not to see things the same way. So that helps us anyway. But as Doug said, these things just crank along, and it finds bugs. Like usually, you know, the developer is like, how in the world did you find this? And it's a little difficult to have to give the answer, I don't know, you know, but it's a bug. And it's just an astounding bunch of stuff. So I have a program called Beeline. So one of the issues with this system is that, you know, there's so many steps in all of this. This thing could run for, you know, 3,000 steps and then find a bug, and no developer is going to fix a bug with a 3,000 step repro sequence. But what Beeline did is Beeline would say, well, I know how the graph all connects and I know what the path was. Therefore, I will follow part of the path and then randomly leave it and choose a shortest distance path to a place further along in the repro cycle. If it doesn't repro the bug, then fine, and I start again. If it does repro the bug, then I now have a shorter path that seems to cause the same bug, and then it iterates. And so Beeline used to bring, these 1,000, 2,000 step repros down to 7 steps, 8 steps. So there's just a tremendous amount of power in these graphs and the information in them and the traversals you can use on them.
Well, thank you, gentlemen. I think we've worked through most of the questions, although I'll bet there'll be a bunch more that we could probably funnel your way if we get them in email form.
Good.
Fascinating discussion. Very much appreciate that. And I wanted to thank everybody for their comments on my unofficial survey. It sounds like some type of hybrid model is definitely preferred and needed, as not everybody is local, but we will figure out a creative way to make sure that we continue to present this to those folks that can't join us. And that, I think I'll hand it over to you, Shelley and or Joe, to close.
Yeah, thanks everybody for joining. Thanks, Harry and Doug.
Thank you.
Thank you for having us.
Thank you
Thank
so
you
much.
for
And I
your
just
time,
have one more quick thing. We're doing lightning talks in July, and we're still looking for a couple speakers. So if anybody's interested in doing a quick, they're about 10-minute talks, ping us and let us know that you're interested. So that's the last thing. But thanks so much to Harry and Doug. We loved it. It was great. Really appreciate your time.
Thank
Thank
you.
you.
It's nice to be zooming with someone else other than Doug all the time.
And then we've also started this new event that goes on opposite months of the QASIG. It's the PM SIG. So it's the second Wednesday of every even numbered month. And that's coming up. So if you're interested in that, just log on to pmsig.org and we'll keep you posted.
All right.
Thanks for being a part of everything.
Yeah. Have a great night, everybody. And thank you for participating.
Thanks.
Thank you.
All right.
Bye-bye.
Take care.